Good evening. Tuma madam,
Yes,
are we going to start the session?
yes, madam. Yes, madam.
Okay, thank you. Good evening, everyone. On behalf of the organizing committee, I, Ruchita Ghoshachra, welcome you all to the ATAL Academy 6 Days Online FDP on Quantum Age Intelligence, sponsored by AICT and organized by the Department of Computer Science and Engineering of MCKVIE Institute of Engineering. Today is the fifth day of this FTP, and right now we are going to start session 9 of this week long program with a lecture on sustainable agriculture with quantum drone. Today, we are honored to have with us Dr. Nurzaman Ahmed, engineering research scientist, Donald Danforth Plant Science Center, St. Louis, United States. Before Dr. Nurzaman starts his lecture, let me take this privilege to introduce him to the audience. Before joining Denmark, he was a postdoctoral scholar at Dartmouth College. He was also a postdoctoral fellow at Indian Institute of Science, Bangalore, and a research associate at Indian Institute of Technology, Kharagpur. He received his Doctor of Philosophy from Northeastern Hill University, India in 2020. He received his BTech and MTech in Information Technology from the Northeastern Hill University. He has started his career as a junior research fellow at Northeastern Hill University, Shillong in 2013. He has more than 50 publications in reputed international journals and conferences, along with several book chapters and patents. His current research interests include Internet of Things, software defined networks, and Wi Fi based long distance networks. He is a member of IEEE and ACM and a graduate member of IEEE ComSoc. With this brief introduction, may I now request Dr. Nurzaman Ahmed to carry out his session.
Thank you so much for nice introduction. Can you please confirm, am I audible or not?
Yes, sir, you're perfectly audible.
Okay, yeah, thank you so much. I'll try to share my screen. Is it visible, my,
Yes, yes, sir.
yeah, the title
Visible.
page, right? Yeah.
Title page is visible.
Okay, yeah,
You
sounds
can
good.
start.
Thank you so much.
Okay.
Yeah. All right. Yeah, good evening, everyone. It's morning here. It's around 7:37. But I know like it's kind of late of the day there. First of all, thank you for having me here today. Uh, we'll be talking about sustainable agriculture with quantum drones. My work has been in the area of precision agriculture, developing technologies to make farming more efficient, sustainable, and productive. However, I am not an expert in quantum computing, but with my understanding of the potential application of quantum computing, I'm quite certain that the complex problem that we have today in agriculture, for example, the climate change, then resource scarcity, this required advanced computing facilities. I think this is where the quantum computing has been explored recently for this kind of problem, like where agriculture's uh, food scarcity problem, especially. Today, I'll start by sharing about some of my work that have been working mostly field-based implementation work. Then we try to bridge those problem and identify some of the problem, and then we try to bridge those problem with quantum computing solutions, like how they can tackle those kind of solutions. All right, so talking about my work here, some of the figures here. So this is my uh, center. It's called Donald Danforth Plant Science Center. They recently they have been working on kind of like sustainable agriculture, not only like improving yield or production with less cost kind of thing that what we understand from sustainable agriculture, but also uh, they're specifically talking about climate change, and then and that way like research has been done on not only above ground, also below ground of varieties of crops. So I've been involved in deploying mostly field-based sensors. of How can we automatically collect huge amount of data from a field location, remote field location in a rural USA agricultural land, using different communication technologies, computation technologies, and then automatically making a kind of pipeline using like wireless sensor network, and then also UAVs. So making that automatic pipeline, solving some kind of, let's say it was like earlier, it was kind of lengthy duration of collecting those data and analysis. But what we do is like we try to reduce that loop of closing and reduce that time loop of that operations. Um, these are some of the sensors that we deploy, which collects below and above ground data uh, on powered by solar panels. Then for below ground data, we have been using some other technologies called mini rhizotrons. So the idea is like, can you collect those data when the plant grows in the real time? All right, so let's go ahead. So today's session we will be having some, like initially we will go through like uh, what is sustainable agriculture through precision farming, then some of the technologies which enable those sustainability is Internet of Things, and then we go edge computing, and then slowly we move to understand how edge AI on drones. Yeah, also before that, we will also see some application how drone can be useful in farming, and then as AI in drones, then we'll go like quantum method. How can we add quantum method in those drone or UAV systems? And then finally, we try to uh, uh, a- propose a practical hybrid. I mean, like the classical and quantum based stack or pipeline, which can be implemented at this moment. All right, so okay, the first question, why now? Food, climate, labor, right? So why do you need this advanced technology? So we've been talking about IoT, edge computing, drone, quantum. So the need is that, as I said, like uh, we are facing unprecedented global challenges. If you see like around like over every day, the climate change is the one of the major factor, like which has been changing drastically. And at the same time, we need food demands. See the food demands. So if you see some statistics which tells that by 2050 there will be 70% more food than currently what we have. So at the same time, what we know is that we have the climate change problem is coming up. Then, but the we have the same kind of arable land, and then fresh water, skill labor. So and then above we have the climate science problem. So and we can see like more droughts, floods, pests, new pest kind of things. They're coming in a huge amount. They're cycling in unprecedentedly. So to tackle these challenges, we researchers have been trying to propose or finding some solutions. Like one of the idea is like sustainability, sustainable agriculture. So where we bring different advanced technologies like like Internet of Things, machine learning, uh, then now like quantum computing to kind of provide a sustainable agriculture, not only to help to increase those 70% requirement, but also how can those crops or how the agriculture can be even the changing climate conditions. As I mentioned about like the pillar of understanding the field environment and then getting more into it to before providing some kind of solution on sustainability. So there is one technology called Internet of Things. When we apply for agriculture, we call it like Internet of Agriculture. This is suitable because like we talk about connecting any kind of things from a particular area of interest and then to the internet. So we are connected easily with our computers, with our laptop to the internet. However, to talk, to understand the field environment, there can be sensors, but to connect those sensors, IoT is uh, here to help. Um, a little bit background on IoT, like it started earlier when there was like only pre-internet time, host-to-host communication. Then we have the internet webcam, and then mobiles can be connected to the internet. That's the first kind of small object things that can be connected to the mobile. But those are again heavy computers kind of. Then people can connect using mobiles or our portable laptop or any computer. Then Internet of Things, where interconnected objects, so anything around we see, those objects started connecting to the internet. But to connect to the internet, we have some kind of capability it should be there. So one of them, they of course like when you connect an object that should be able to sense smartly. So sensors, sometimes those objects can act as well, like it's called actuator. And then they should be able to internet is like there is some kind of a stack is running which is identified some addresses, so they should have some kind of unique address to that so that the internet can identify them. So so these are the features should be there on those objects, and then we say it's the internet of things. So in a cycle in an ecosystem where things are connected to the internet, and then data has been shared among them. So there some of the examples, like when you we can buy Arduino or any kind of devices where we connect a sensors using the GPI exposed GPI port, and then we can read a port. So per port, a port become a things here, and then it can tell the information about how much, what is the soil moisture level or any kind of information on that. And similarly, a actuator can relay or start a water pump or stop a water pump. So that's the actuator. There are many kind of other devices as well. They work on state, for example, GPS, or they works like state, chance of state kind of. So if you see the architecture, it mostly have three layers. Perception layer, where sensors are actually are there at the ground level. And when this communication stack of the device, it helps to connect other devices and forward the data or receive the data from a networking stack. So that's the network layer where device helps to forward, receive, transmit the data. to the internet and vice versa. At internet, we have the cloud where we can implement our application based on the data or try to control those devices or objects in the perception layer. An example that we can right now implement is that, like, let's say we have like a Raspberry Pi device, which is very common, and then can be used kind of a gateway, which is gateway mostly need to have some kind of one of the main features is to kind of providing an interface between upper layer, like application layer, and the perception. So it needs to have capability of receiving and transmitting data. So then, like, again it is IoT is like kind of heterogeneous, like it can have multiple, there is no standard way to specifically communication kind of thing. So they can have multiple communication technology, for example Bluetooth, Zigbee. So then gateway should have multiple interfaces. And as well, like when it forwards data to the cloud, it needs to have some better connectivity so that they can send more data or receive more data from there. So there should be both way communication. So that's there in Raspberry Pi. Kind of you can attach a USB cable for some other communication, or already built in Bluetooth and Wi-Fi are there. So those can be used for enabling communication with the devices. So this is one of the device. It's called Node MCU. It's very cheap. You can buy. We can create a sensor module. We can create an actuator module. They can be connected to a Raspberry Pi, and then from there we can. It can be. We can further communicate for application deployment, hosting some web server or application server in the cloud, and we can do it. So here we are trying to develop a plane care game, how to simulate a plane growth, and then how to optimize the water level and other nutrient level of that plant. So that kind of examples we did create for showing up like how IoT can be used for precision agriculture. So we are talking about the data collection from the field, which is very critical. Now, when you talk about agriculture, we mostly think that the field environment, right? So in the rural environment, so this is generally not close to a infrastructure, maybe communication infrastructure. So hardly there are communication facilities available in a rural place. So farms in the remote areas with limited connectivity make the data transmission difficult. Then bandwidth constraint is there. When you talk about, again, the same problem, that remote location, we hardly have some network infrastructure available there. So bandwidth is another constraint. Large, generally field used to be very large in area, where to get all the data from a field, we need multiple significant number of devices should be there. And then it's very challenging kind of deploying a wireless network and maintaining it, most importantly. Data integration gap, lack of standardization create fragmented information across devices. And then environmental challenge, that's one of the huge, like when because of extreme weather changes, like soil condition, water expert, rain, storms, those creates problem for data collection from a remote field environment. So in our work, I've been working on this area since my PhD time, before PhD as well. So one of the work that we propose is like how to connect, how to provide an end-to-end scalable connectivity solutions with recent some of the computing and communication technology. So in Indian, especially in Indian rural places where communication is a huge problem there as well. And then we needed to find some kind of low-cost solution. So we propose an end-to-end scalable connectivity solution. At the same time, due to the longer coverage and other issues, decision making is an important aspect, which then we propose like some kind of work computing based approach, which can help in making decision and doing some kind of competition with, and that ultimately help to reduce the uplink bandwidth and reduce the latency. So this setup has been practically deployed for prototyping, and then we did some stack-based modification in network level Wi-Fi protocol. We modified the Wi-Fi protocol to support longer range communication in a point-to-point setup. Then in the field environment, because this we can in the backbone we use Wi-Fi, and then in the field we use 6LoWPAN, which is based on IEEE 802.15.4 for low power communication. So selection of those technology for sustainability, not only like crop level but also stack or pipeline is very important. That's the reason. Or feasibility is another case. So we have to select some communication or some technology which is low power consuming in the field. So we modified MAC protocol for wireless sensor network to support multi-hop communication within the field, and then also some sort of, because we are talking about multi-hop, so low latency, to reduce latency and increase bandwidth, we needed to have like sufficient efficient protocol which can utilize less resources and increase the bandwidth. So with that, we deploy in this scenario. This is like near to the Northeastern Hill University, that where I did my PhD, and then there is a gateway network which is connected to the internet, and then because of the hilly terrain, we needed to deploy some other relay nodes for line of sight. So it goes from here to there and there, and finally from this place there is some paddy field. So we try to connect those paddy fields with multiple sensors deployed there for prototyping. And these are the nodes. So there is the omnidirectional antenna, and then these are the directional antenna. So omnidirectional antenna is the n mile connectivity covering that particular area, which has opposed lesser range. And then directional antenna, while we use narrow beam width for covering longer range, but at the same time a MAC layer modification has been done to support multi-hop and a new MAC protocol, which is proposed here. The idea is like it's kind of time division multiplexing, but what we try to do is we synchronize those nodes in multiple hops, and then we switch transmission and reception mode so that we can receive we can receive a non-interfering transmission, but only using 2 slots. So that way we are increasing the bandwidth and transmission bandwidth for a multi-hop Wi-Fi based long distance network. Similarly, for wireless network, we are uploading data from multi-hop to the gateway. So we consider some of the properties of a cross-layering routing layer. We went to upper layer and find out the rank of this particular devices, and we try to make a time schedule which is based on the rank. So basically what we're saying is that if the rank value is higher, the sampling duration would be, so sensing duration would be more because it has more nodes sensing the data. So this way we achieve some better performances in terms of collecting end-to-end data. At the same time, we, as I said, like at the backbone, every router has kind of computing capability, these nodes. So we deploy some computation which do the required calculation. If not, it forward to the parents of that particular device. So we do some computation here. So if it is already loaded, it can offload some tasks to its parents for compromise latency or bandwidth. Okay, so after in coming here, we have been trying to, the challenges that we found is that like how to make a hardware and software based solution which is practically can be uh, uh, applicable for longer time duration. Let's say we keep some devices in the field for like 4 or 5 years continuously, and then they give the data. So we needed to come up with some idea which proposes to make a strong hardware setup which exist even there are harsh weather condition or something, as well as uh, how to reduce the complexity in the field and bring all kind of management practices, device onboarding, then all the required complexities which is to be there in a wireless communication system towards to the cloud-based application layer. So kind of software-defined approach, like where configuration has been done on the data plane, and then we do connect it to the control plane for doing all kind of management operation. So this is a setup called FinOD, where gateway, it has like gateway and gateway means like it has the capability of connecting all the sensors locally available using LoRa or Bluetooth, and then forwarding the data using Wi-Fi if it is there. Otherwise, a cellular modem can help to upload the data. So the main target was like how can we deploy multiple weather and soil related sensor in it, and then how to keep this device alive for longer time, even any kind of weather conditions. So this can help in outdoor phenotyping. So if you need to get data in a indoor and outdoor, so in outdoor condition, let's say this kind of large area field where we can have those small wireless sensor deployed, they're connected to a single FinOD gateway for uploading their data, soil or weather related data, to the gateway, and gateway can further help. So that way we can have a distributed long range communication enabled by those FinOD and wireless sensor. Even the Bluetooth communication technology can further help to connect all the research facility within a greenhouse as well, or maybe not maybe specifically research facility, but also any kind of that kind of area where we need to collect those data. Then so some sort of interface, as I said, like can we not only see the data but also some kind of management operation that we do, so that device onboarding, then troubleshooting those devices, uh, connecting Wi-Fi, communication, routing, those we can, this GUI system can help with that as well. So those devices can also collect visual like images for analysis in the cloud. So in the later phase, we found that like the communication technology, there is a gap. Like, so some of the communication technology for the Wi-Fi, or even if you see here, like we generally we divide this whole communication like in this category, like local area network. So if you see on power speed on the y-axis and the distance on x-axis, so generally personal area network, like so it's basically the smaller communication is like Bluetooth, Thread, Zigbee, they are like on 30 meter maximum, sometimes 10 meter. So they need, if we deploy them, we have like less coverage, less power, that's good, but for longer coverage those are not suitable. So we have like LoRa or Sigfox is called low power wide area network. They are been recently very popular, and then they people are using. The problem with them is that like they can transmit only very tiny bit of data. So in case like where you need to transmit like images or some kind of other larger size data, so they are not suitable. And then Wi-Fi, they are very power consuming. it's difficult for field environment, especially when you think about the like solar powered kind of solution. And then WAN is like mostly cellular LTE 5G kind of communication technology comes. So we need when you find some kind of solution within these regions. So then we found that there is a not recent, but one communication technology from IEEE that's called Wi-Fi Hello. It's the IEEE 802.11ah. Like we know 11A, B, Z, right? So then AH is that one. So that was specifically proposed for IoT kind of environment where we connect this communication technology other than like those traditional Wi-Fi, they works on like 5 gigahertz, 2.4, but this one in sub 1 gigahertz. So this is the range towards like LoRa, how LoRa and Sigfox works, like 900 megahertz and below. So the advantage of this communication channel is that it can cover longer range, but IEEE is the idea of it is that how to connect a large number of devices, specifically like smart city or smart agriculture, where uh, large number of that kind of devices will be there, and then communication range is higher. So this communication with sub 1 gigahertz, it can cover up to 1 kilometer just in a single hop, and then we can connect 8,000 devices in just a single access point. So that's support is there. So, and then there are many other advanced features like grouping, restricted access window, because when you talk about large number of devices, there should have been some kind of restricting of simultaneous transmission and reception. So that kind of advancements are there. So we initially took that idea of how can we implement any remote Wi-Fi halo network, but can we manage that network as well? So we consider software-defined base approach. So we then try to understand like traffic pattern in agricultural application, and then predicting those kind of application traffic pattern. If you know it, then we can dynamically schedule those networks for saving energy, reducing latency, and improving the throughput. So that was the target of this kind of that work that we did. So in data computing, we've been talking about data communication. In the data computing, there is also challenge. One is that latency sensitivity. Some of the decision making should be very uh, low latency consuming. Real-time decision required low latency computing in resource constrained environment. Data overload. Large-scale farms generate enormous data volumes, challenges the process efficient to process efficient. Then when you keep those, of course, like if it is a sensitive data, security, privacy is one of the important parameters. But in IoT, which has been a huge challenge till now because of lack of standardization, and also because of easily exposed, because when you keep a device to the outdoor in the field, it's exposed to anyone, and then so security privacy concerns are there. Resource constraint, they have limited computation power, storage energy, so they cannot do lots of the operation there. It's locally. Cost of infrastructure, establishing as cloud infrastructure in rural areas is expensive, as I said, because of the backbone. There is a huge difference between the cost and the production kind of thing. So mostly I see in the research kind of uh, activities, we see where people deploy the costly infrastructure. So here in Danforth, we came up with some idea which is based on edge computing. So when you try to collect large amount of data, including sensors, images, huge amount of image data, larger file, and then it's totally almost impossible to transmit those data using a LTE cellular, which is even having very low signal quality. Then what to do? We can keep a device locally on the field, So, and then that device do some of the processing or based on those images and send only the information that we required from that particular experiment or that from those data. So this is where we propose field dock, a docking system enabled by edge computing at the field. It remains at the field, which is like a UAV drone. There can be multiple drone flying around, but only one place to stand and get docking. So once it dock automatically through the lag, there is a uh, contact based charging. So it get automatically charged on uh, a magnetic base automatic charging platform, and then it's called charging station. Then C is that's the gateway or node that we are keeping, which is helping us to connect all other sensors here, getting data, and also providing an infrastructure for communicating other component like the SkyChar, this charging platform, then edge computer and other devices here. Battery is there, then edge computer, which is where we're doing the computation, and there is a solar panel for providing all the energy required for this all computing system running here. So there is a video just wanted to show how the mission is completed. So our target is like getting lots of data and we do phenotyping. So in a particular area where you have multiple varieties of same probe, and then we get UAV wireless sensor data, analyze them, and this data has been further given to a genetic analysis where you do mapping between phenotyping properties with the particular genotype. So I want to play this video. Just 2 minutes, I think. Let's see it. Yeah, so ultimately we can have some kind of orthomosaic figure like this. So for example, this is one of the figure that we collected using that system where we have multiple varieties of sorghum. And if you see that, interestingly, this is collected by the multispectral camera. There are different colors. So those spectral sensors, they work like they provide you uh, different colors on then, or we can understand, we can profile different properties, and we can map ultimately to a different all genotypes, and then this is very helpful for understanding and phenotyping the crop varieties. So we, as I mentioned, that we use edge computing in field dock. So edge state, there is a state machine which orchestrate the sensor data collection, UAV operation, real-time analysis for efficient workflow. A software to call Open Drone Mapper, which processes those images collected by the drone and then generating orthomosaic 3D model plot indices. And then locally, we also do downsampling to optimize data size and the cloud transmission. Key benefits are, one of them is like efficiency. We process and analyze data locally to minimize latency. So we found that almost like the whole end-to-end operation, it was like traditionally, even with UAV, it used to be like 1 week. Now we can do it in like 4 to 5 hours. So we have significantly reduced the latency, end-to-end latency. At the same time, we also reduce almost 90% of bandwidth, because we do lots of data we keep locally and we only send the output data. So we reduce the data, uploading data, scalability and resource optimization. Okay, so coming to the point about what drone brings to the farms, as I said, like it has the capability of controlling flying around the field area, and then we can deploy multiple sensor system and cameras in those drone, which can be very useful for collecting data of different uh, channel range. For example, spectral cameras like multispectral, hyperspectral, RGB cameras, we can fly over the field on demand and then collect high resolution data. We can also do like precision plot level scouting, variable rate spraying, or in kind of yeah. So along with collecting data, actuating is another big advantage. So connecting some kind of accessor, for example, spraying or spraying seed or spraying fertilizers, or sometimes even harvesting. I see many videos coming up where people uses drones to harvest like apple or other kind of fruits from the tree, as well as uh, spraying water as well. So this kind of lots of use of drones here, and which is not possible like manually going human be there and do those kind of operation. And then onboard computing facility. So we, in our system that we use, is a Jetson Nano to also land precisely on a particular place. So GPS has the accuracy issues, so we kind of there is a particular picture we kept in the ground, and then the camera sees the picture real time and try to adjust its axis or landing, so ultimately helping the drone precisely at that place. So this kind of complex operation can be running a machine learning model also can be possible on board. So that's a huge advantage. And then coverage, repeatable, time aligned passes when phenotyping to many kind of operations, which is possible. Yeah, so coming to the challenges of drone. So look at the diagram showing a typical agriculture field with sensor drone scanning crops, then communication nodes coordinating their movements, and then target zones, intervention, and crop are being monitored, right? So in that case, there are some of the optimization challenges are there. So one of them is like long-lasting problem is that real-time path planning, which requires lots of optimization, uh, optimizing routes, basically like where to fly, how, especially when there are multiple drones. So their communication path need to be optimized, considering that there are obstacles. They should not be colliding. There can be some obstacle, and then maintaining efficiency. So their use kind of optimization problem is there. And then second, sensor data fusion. So we are talking about multimedia, sensors, heterogeneous data, and then which is a huge problem that need like special kind of computation here too. Obstacle avoidance demands instant decision in complex kind of, let's say if it is a 3D environment, so problem become more complex. Then most importantly, when there is a drone of swarms, synchronizing hundreds of drones for coordinated tasks is very important. Weather adaptation, real-time adjustment to wind, temperature, and other data, and precision agriculture, of course, analyzing agriculture data for targeted COVID. So in these challenges, you see lots of optimization, lots of iteration need to be done in the middle. So needs huge computation capability. This is where I think we are talking about like quantum computing. Um, uh, I'm not, as I said, I'm not an expert of, but fundamentally, some of the properties I think everybody we know is basically unlike classical computer where 0 and 1 are the main bits, but here they call it qubits. Like, so the idea is like even those qubits can exist in superposition. Superposition means like it can be being both 0 and 1. So this is where the interesting thing is like, so, and then some other properties like quantum entanglement where they the state of those qubits shows correlation among them. And then so these are some of the basic features, but I think there are some other like error corrections and then interference. Those properties are very important as well. So overall, what I want to say is that like uh, when we measure this superposition of those state, they collapse to either 0 or 1 with a certain probabilities as output, right? So and then what is as a researcher, they try to bring out probability to a particular using many approaches. They bring out the probability of a targeted operation to higher, right? So but during this computation, each qubit explore multiple possibilities at once. So in between, like at the end, they ultimately become a classical 0 and 1 with probability, but in between they do multiple possibilities, explore possibilities. So this is why the quantum computing can solve optimization problem very nicely as compared to the classical. So as they do the all combination at the same time, they can see those kind of optimization problem and finding, and we can redirect or program it to make it to a particular problem with a probability. So that shows like how it can solve this particular problem efficiently. So that's very interesting, and then that's why people have been started talking about how can we deploy some kind of complex application like drone deployment, swarm of drone, and especially in agriculture when we talking about when we are talking about data collecting huge amount of data from large field heterogeneous data, and then there are multiple drones, multiple data, uh, different kind of environment obstacles. So this is where I think quantum computing can help to the drones for their operations. In edge intelligence also, so we keep latency critical perception tasks right on the drone itself, generally what we do. And then for harder kind of optimization, this quantum computing can help so drone can offload those kind of tasks, maybe so something let's say decision making. So of course like it's difficult to deploy a quantum module at the drone. So then in the cloud level or other places there will be the quantum, and then when the data will be sent or for optimization, the drone quantum module can give a solution to those drone for that problem that we have been discussing. So where quantum fits today, as I said, routing, scheduling, multi-drone path planning, refill, no-fly zones, then resource allocation, variable rate prescription under constraints, then feature selection, model search. So small kernels or QML prototypes are been people have been working already. Secure communication, this is one of the popular area. People have been working as well in cryptography. Quantum computing is a different level of advantages there. So overall, what we can right now at this moment we can propose is that kind of architecture which is hybrid, and then here like the quantum module of course should be close towards the cloud or high processing computing facility in there, and then it can do those there are existing algorithms already available for optimization, and then it can help with those algorithm to the problem that right now a drone required. So we have like sensors, we have perception, safety, control, uplink, communication. They use those data to upload and then need to optimize something, and then intermediate local ads gateway can be further helpful for transmitting, processing those data towards the cloud, and then cloud can help with the quantum module which has already some existing algorithm, and then it gives a better the best solution for the drone problem that it's been facing. Yeah. All right. So the key takeaways, I think when we started talking about sustainable farming, uh, one of the things that important is like optimizing resource allocation and reduce chemical uses. Scalable solution work for small farms to large agriculture operation. Then edge computing and then use of AI locally at the edge can further help in decision making, also predicting various requirements and then application requirement as well. When we talk about multiple drones, their communication, obstacle, efficiency, planning become some of the huge problem. This is where quantum computing can solve those complex problem that classical computer cannot handle efficiently. Then we propose a hybrid architecture where classical architecture, but with a connected quantum module with existing or optimization algorithm that can already solve some of the problem if you can connect seamlessly those systems, those field-based system as well. So if you can make the pipeline, that can already been helpful for optimizing some of the problem already. Yeah, thank you. If there is any question, I'll be waiting for chat here, or I have my email address here. Please feel free to reach me anytime. I can get back to you soon. Thank you so much.
Thank you, Dr. Nurzaman, for your wonderful speech. Participants, if you have any question, you can unmute yourself or write in the chat box so that Dr. Nurzaman can answer your queries.
Yeah.
Mr. Sob Ali Khan, your video is on. You want to ask any question? Any one of the participants? If you have any queries,
Yeah, even they can email me anytime. I'll get back quickly as soon as possible for any kind
okay,
of
sir.
queries on the class. Yeah.
So, till now, no queries are coming up.
Yeah.
So, so if participants do not have any queries, Shoma madam, can we stop this session with a big thank you, Dr. Nurzaman Ahmed, who took out time from his busy schedule. Early morning, he woke up to deliver this lecture. Though we are here, it's evening, but
Yeah.
he has to get up early morning and deliver the speech before he resumes his regular duties. So,
Yeah. Yeah, it
thank
was a great time. Thank you so much. Yeah. Yeah,
I think,
should we
yeah,
stop maybe? Yeah.
maybe, sir. Thank you. Thank you so much.
Yeah. Thanks everyone.
Oh,
Thank you so much, man. Yeah. Bye. Thank you so much, ma'am.
okay. So, madam,
Yes, madam.
then we are stopping this session. Maybe we
And
will start at
7:30.
7:30 because,
7:30.
yeah. Okay. Thank you. Thank you so much. Participants can have a tea break by the time we join for the next session. Thank you. Thank you for joining us.